system clock options. So that's the topic of today. We will mainly focus on Atmega 328p clock system. Okay. There are many ways you can generate the system clock. Okay, there's many ways you can do. If you recall your AC lab, you have designed the AC circuit, conductor and capacitor. Okay, capacitor and conductor AC circuit. Okay, what they do? Let's say the capacitor is full of charge, and you connect the inductor. Capacitor will get discharged over the inductor, and inductor will store the energy. After the inductor is fully stored the energy, again it will release the energy, and capacitor again will get charged. Charge and discharge. It will create a sinusoidal oscillating signal. Okay, sinusoidal oscillating signal we have done in AC lab. Okay, if you recall the device lab, you have designed 555 timer. If you recall the device lab, 555 timer, and you have seen the operation of astable multivibrator. What the astable multivibrator does, it generates a sequence of clock pulses, a square wave, high low high low. Astable mode of operation of 555 timer. So these are the different way you can generate the clock signal. Okay. Every microcontroller needs a clock source. The CPU, the memory bus, the peripherals, clock signals are everywhere inside a microcontroller. They govern the speed at which the processor executes instructions, the baud rate of serial communication signals, the amount of time needed to perform analog to digital conversion, and so much more. Yes. All these clocking actions go back to the source of the clock signal, namely the oscillator. Therefore, the oscillator must be able to provide the desired performance from the microcontroller. Though some oscillator options are more complex or expensive than others, so the choice of oscillator should reflect the importance of reducing cost and complexity whenever possible. Now, for a given microcontroller based system, there may be different source of the clock or different oscillator that supply the clock. Which one you will pick up? That depends on the cost and complexity. Okay. CPU clock speed is a good indicator of the processor performance. In general, a higher clock speed means a faster CPU. A CPU with a clock speed of 3.2 GHz executes 3.2 billion cycles per second. Very high speed. There are quite a few ways to generate a clock signal for a microcontroller. The datasheet of the microcontroller should provide a good deal of information about what types of oscillators can be used and how to implement them in a way that is compatible with the hardware. Now, when you want to deal with a particular microprocessor or microcontroller, the first thing you need to consult the datasheet. Datasheet has the detailed description of different way or different type of microcontroller, how you incorporate, okay, all the information for your implementation you can find from the datasheet. So datasheet is the first place you should start. For today's class, we have done the same thing. We have used the datasheet and we have summarized the main information from the datasheet in a PowerPoint slide file so that we can cover in the class. Otherwise, Datasheet has all the detailed information. After the class, if you want to go in details, check the datasheet. Okay, it's widely available. I have already downloaded it for you, but if you want to download it by yourself, just give a search on Google Atmega 328p datasheet. Okay, and it has all the information. I'll show you. Okay, I'll open the datasheet and I'll guide you through the datasheet. There are some advantages and disadvantages of various clock sources, and thus it is needed to choose the best one among the oscillator options available for a particular microcontroller. So there can be several options available, but depending on your requirement, you will choose the right one. There are two broad types of oscillator, internal and external. Some oscillators come built in with the device, and some oscillator you can add externally. Okay, depending on your requirement. So internal oscillator example like this, a resistor capacitor circuit RC phase shift oscillator circuit, phased lock loop PLL for frequency multiplication. Okay. Example of external oscillator, CMOS clock, crystal oscillator, ceramic resonator oscillator, resistor capacitor oscillator, capacitor only oscillator, etc. So many ways you can implement the oscillator. Okay. Look at over here. Look at the diagram. The bottom part. This bottom part. Several oscillator option. Timer counter oscillator, first one. Then external clock, crystal oscillator, low frequency crystal oscillator, then calibrated RC oscillator. Okay, we will go in details. Okay, basically by default for Atmega 328p microcontroller, by default it is set to use this RC oscillator, calibrated RC oscillator. This oscillator run at frequency 8 MHz by default. Then it uses a system clock prescaler to divide this 8 MHz by 8, and it gets 1 MHz clock. And initially, if you don't do any modification in the register set or internally, your system will run at 1 MHz system clock by default, unless you modify it, unless you modify the setting. Okay, so there are several oscillator options, and you can choose a particular one depending on your need. The block diagram represents the principal clock system in the AVR and their distribution. All the clocks need not to be active at a given time. You see, there are many different sources, but you don't need to activate all the sources at a given time, because all the unit consume power. You see, if you activate all the unit at the same time, what will happen? You don't need it. You will just waste of energy. Only you activate the module that you are using. That's all. Okay. To reduce the power consumption, the clocks to module not being used can be halted by using different sleep modes. We'll talk about the sleep modes. By using different sleep modes, you can halt some of the components or some of the functionality of the microcontroller to conserve energy. Halt means, let's say, suppose while you are sleeping, similar like you are sleeping. Halt is similar like it is sleeping. Now there are different options of sleeping. Depending on the option you choose, some sleep mode will give you more saving in energy, some sleep mode will give you less saving of energy. It depends on the features and option that you select. Okay. Why sleep mode is important? Suppose you have designed a gadget by using this microcontroller, and you want to sell that gadget in the market. If your device consume a pair of pencil battery every day, anyone will buy your project? No, because to make your system running, they need to purchase pair of battery every day. Not practical. Instead, what you can do, you can use the sleep mode wisely, and you can extend the battery life, let's say over 3 months or 6 months, even a year. It is possible that you can extend a single pencil battery over the year. One pencil battery over the year. People will go for your device because yes, it does not need to change the battery every day. Just once a year you change it, or once in a 6 months you change it. Okay, so to design a power saving, that means that is power friendly application, you need to use the sleep mode properly. So today class will introduce you with the sleep modes, and when you write the program, keep in mind when you go for actual production, make sure you properly utilize the sleep mode for reduced power consumption or power friendly. Okay, so that people don't need to change their battery every day. Okay.
Is there any system which doesn't require sleep mode?
If you don't sleep, for example, then it will use the full power continuously. Then a single day it will exhaust as pair of battery maybe. Yes, every day you need to change the battery because you are running the full power option. Okay, not quite practical. Then people are not going to buy your device. Okay, so make sure this is a very important topic that we are going to cover today, and you need to consider this situation when you go for actual production, want to sell your product in the market. Okay. So to reduce the power consumption, the clocks to modules not being used can be halted by using the different sleep modes. So look at just let me summarize this picture. Okay, I think I have a better picture than this one, a colorful picture. So do you want to see that picture? So let's open the data sheet. So better open the data sheet. Data sheet has the colorful picture. Okay. Okay. This is the data sheet. And you can download this data sheet from the net. Okay, just give a search Atmega 328p, you can download it. So we are covering the topic of 2 days from chapter 13. Look at over here. What is chapter 13? System clock and clock option. Page number 48. So let's go to the page number 48. Look at the picture. A colorful picture. Okay. So look at over here. These are the different source or oscillator, clock generator. Okay. And at a time, you pick up only one oscillator or source. So this is the clock multiplexer. So you just take your digital output and feed that output to the system clock press color. For example, this is by default calibrated internal RC oscillator. It runs at 8 megahertz. So when you feed this 8 megahertz to the system clock press color, it divides this frequency by 8 by default. By default, okay, it is pre-programmed. It will divide by 8. You can change it, okay, but by default it will do divide by 8. So when you divide by 8, you get a system clock of 1 megahertz. So this 1 megahertz frequency comes to the AVR clock control unit, and this unit supply that frequency to different functional block of the microcontroller. This is the asynchronous timer counter. It's the clock. All run at the same frequency. Okay. This is a general I/O module. Clock getting supplied for over there. Analog to digital converter. Clock is supplied over there. AVR CPU. This CPU is getting the clock. RAM is getting the clock. Flash and EEPROM, EEPROM are getting the clock. All the functional unit, they need the clock to operate. Okay, all the functional unit, they need the clock to operate.
Sir, in this sector, can you consider it as a output?
This one,
Upper portions.
upper portion, they are the different component of the microcontroller. They are inside the main CPU or main microcontroller unit. They are the different functional block of the microcontroller. For example, let's say asynchronous timer counter. Okay, this is another timer counter we have covered in the last 3 class. Okay, timer 0, timer 1, timer 2. Timer 0, timer 2, they are 8-bit counter, and timer 2, 16-bit counter. So they are asynchronous. They work asynchronously. To work, they need the clock. So they get the clock from the AVR clock control unit. Second block, general I/O modules, input-output operation. Again, they need the clock to perform the operation. Analog to digital converter. Suppose you want to sense the analog data. All the data you see in the environment surrounding, all are analog information. Your computer or CPU, you need digital device. Your CPU cannot understand or read analog data. They need digital form of analog information. So how we convert this analog information to digital? By using a device called sensor. Sensor sense the analog data, then sensor convert that analog data to a voltage form in the range of 0 to 5 volt. Okay. Now this voltage gets sampled by the analog to digital converter. When you sample this voltage, you see, for Atmega 328p, they use 10-bit ADC. Okay, so they have resolution 1024, 10-bit ADC, 2 to the 10. So they sample this analog voltage by the frequency. At what frequency you supply? The more frequency you use, the more accurate result you will get. Okay, that means more sampling. You see, if you sample more frequently, your data will be more quite accurate. Okay, so that depends on the frequency. Okay, at what rate you are sampling, and they use the analog to digital converter 10-bit. So for the sampling operation and for the conversion, they need the clock signal. Okay.
Is sampling and conversion two different things?
No, this is simple. You see, by using sample, you see, you get the data. Let's say 0 to 5 volt, you get sample of our in a range. Every value, let's say 0.1, 0.2, 0.4, 3, 5. Okay, every value get converted to a digital value in between 0 to 1023. Let's say 5 volt has a digital value of 1023. Let's say 4 volt, you can divide. Okay, 0 volt is 0. Okay, 2.5 volt, 511. Okay, so 0 to 5 volt get converted in a range between 0 to 1023 because it is 10-bit ADC. Okay, so that's the job of ADC. You see, when you convert, then you know you can analyze that information. Then you know that let's say if the intensity of the light is let's say maximum is 5. If you get a value 1023, then you can know that microcontroller knows that this is maximum intensity. If it is let's say 50%, 2.5, then you get a value around let's say 511. Then you can know 50% intensity. If you get a value 0, you know that no light, complete darkness. So that's the way your computer can analyze digital value. not analog. Okay, so we convert the analog to digital by using the sensor, and the sensor give a voltage output at the microcontroller pin in the range in between 0 to 5 volt. Now you sample that voltage. Okay, you convert that voltage in a digital form. Okay, so that's the reason we need the clock for it. Okay, now AVR CPU, the main brain, they need the clock to operate. Okay, there are, I think, control unit. Okay, they generate the control signal, they need the clock. ALU, for the ALU operation, they need the clock. Arithmetic logic unit. Okay, this is the RAM, random access memory. You read and write data to the RAM. You need the clock for read write operation. Flash and EEPROM, again, you need the clock. Everywhere, that means they are the functional block inside the CPU. For every functional block, you need the clock signal. So it is like the heart. Okay, it is like your heart is pumping the blood continuously. Similar way, you need a continuous supply of clock for the microcontroller or microprocessor to operate. So oscillator is very important. So this is the way your oscillator works. These are the external oscillator you can connect over here. Okay, it's a low frequency crystal oscillator. So if you look at the data sheet, they have the detailed description of every term, like CPU clock, this is the name. The CPU clock is routed to parts of the system concerned with operation of the AVR core. Examples of such modules are the general purpose register file, the status register, and the data memory holding the stack pointer. Halting the CPU clock inhibits the core from performing general operation and calculation. I/O clock. The I/O clock is used by the majority of the I/O modules like timers, counters, SPI, and ESRT. The I/O clock is also used by the external interrupt module, but the start condition detection in the USA module is carried out asynchronously when clock I/O is halted. TWI 2-wire interface, I2C connection, address recognition in all sleep modes. Okay. So you can find the detailed description of defined functionality over here. Flash clock, asynchronous timer clock. The asynchronous timer clock allows asynchronous timer counters to be clocked directly from an external clock or an external 32 kHz clock crystal. Look at over here, if you look at the picture. Timer counter oscillator. A separate oscillator you can use for it. Okay, a separate oscillator you can use for it. The dedicated clock domain allows using this timer counter as a real-time counter even when the device is in sleep mode. Suppose you have put the device in sleep mode, the device is sleeping, but it can also operate, okay, asynchronously. ADC clock. The ADC is provided with a dedicated clock domain. This allows halting the CPU and I/O clocks in order to reduce noise generated by digital circuitry. This gives more accurate ADC conversion result. Okay. Clock sources. Now, the device has the following clock source option, selectable by flash fuse bits as shown below. Okay, that is a register, and in that register you can set or reset different bits. Okay, the clock from the selected source is input to the AVR clock generator and routed to the appropriate modules. So this is the clock selection bit position 0 to 3. Okay, this is the device clocking option. So depending on the bit you choose, you can pick up different device clock generator. Okay, these are the bit sequence for it. For all fuses, 1 means unprogrammed, and while 0 means programmed. On that register, if you give a 0, it is programmed, and if you give 1, unprogrammed. Default clock source. If you don't do any other change, just get the hardware and work with it. That's the default option, right? So the device is shipped with internal RC oscillator at 8 MHz, and with the fuse clock division 8 programmed. Let me show you this register that where you set or reset the clock. This is taking a little bit time to load the picture. Look at over here. This is the register. Are you set or reset the bit? Clock division 8. By default, it is programmed. Initially, it is given set to 0, reset to 0. Okay, so that 8 megahertz will be divided by 8. Clock out for unprogrammed. This is the startup time. Why we need the startup time? Because you need to have a stable operation of the oscillator. When you turn on the system, oscillator start functioning, and they need to go to a stable situation to be reliable, right? So you need some startup time is get from here. Now this is the clock select 0, clock select 1, 2, 3. By using this 4 bit, you can define the clock source. Initially, by default, it is 0, 0, 1, 0. If it is 0, 0, 1, 0, then it select the internal 8 megahertz oscillator. So that's on the data sheet. So the device, look at over here. The device is shipped with internal RC oscillator at 8 megahertz and with the fuse clock division 8 programmed. That means it is 0, resulting in 1 megahertz system clock. The startup time is set to maximum and the timeout period is enabled. Clock select 0010, startup time 10 and clock division 8. Look at the picture. 0010. Okay, 8 megahertz clock source. Startup time 10. You see, start time 1 and time 0. Bit position 5 and 4. It is 10. This gives maximum startup time. Okay, and now this is clock division 8. That means to divide 8 megahertz by 8 to get 1 megahertz. Okay. This default setting ensures that all users can make their desired clock source setting using any available programming interface. So if you want to change this default option, you can, by using programming, you can change the default setting. Clock startup sequence. Any clock source needs a sufficient VCC to start oscillating and a minimum number of oscillating cycles before it can be considered stable. Okay. The main purpose of delay is to keep the device in reset until it is supplied with minimum VCC. The delay will not monitor the actual voltage, so it is required to select a delay longer than VCC rise time. Okay. The oscillator is required to oscillate for a minimum number of cycles before the clock is considered stable. An internal ripple counter monitors the oscillator output clock and keeps the internal reset active for a given number of clock cycles. The reset is then released and the device will start to execute. Okay. The recommended oscillator startup time is dependent on the clock type and varies from 6 cycles for an externally applied clock to 32K cycles for a low frequency crystal. Okay. so that you get an stable and reliable operation of your microcontroller. Let's go back to our slide. So already have seen this one on the data sheet. The device has the following clock source options selectable by flash bits as shown. The clock from the selected source is input to the AVI clock generator and routed to the appropriate module. This is by default, okay? 0010 is by default. So this is the default clock source. The device is shipped with an internal RC oscillator at 8 MHz and the fuse clock division 8 program, resulting in a 81 MHz system clock. Okay. Now, overclocking can yield improved floating point operation per second, even for high-end CPU like the latest Intel Core i9 processor. Now, sometimes you overclock your computer. Why you overclock your computer? From the bus setting, you can overclock. That means you increase the frequency. What is the advantage? You get smooth operation of your game, right? When you play the video game, you get a more smooth operation, but it consumes more power. Okay, so that term overclocking refers to speeding up the CPU clock for more processing power. The Intel CPU with a K in the name have an unlocked multiplier for easy overclocking when paired with a motherboard chipset that support overclocking. Okay. So overclocking can yield improved floating point performance per second even for high-end CPU like the latest Intel Core i9 processor. Low power crystal oscillator. We have seen there are low power crystal oscillator. Pins XTL1 and XTL2 are input and output respectively for an inverting amplifier which can be configured for use as an on-chip oscillator. Okay, and this is the frequency range. Depending on the desired frequency range, you need to pick up the required capacitor value, and this is the clock select pin configuration. If you want the frequency range 0.4 to 0.9 megahertz, then this is not important, okay? But clock select pin should be 100, pin number 321. If you need the frequency range 0.9 to 3 megahertz, then capacitor C1 and C2 they are 12 picofarad and 22 picofarad, okay? And this is the sequence of clock select. If you need a frequency range 3 to 8 megahertz, then this capacitor C1 and C2 should be 12 to 22, and this is the clock select pin. If you need a frequency range 8 to 16 megahertz, then capacitor C1 is 12 to 22 for C2, and this is the 111 for the clock select bit. Okay. Full swing crystal oscillator. This crystal oscillator is a full swing oscillator with a rail-to-rail swing on the XTL2 output. This is useful for driving other clock inputs in a noisy environment. If you have a noisy environment, then you go for full swing crystal oscillator, and this is the frequency range for it, 0.4 to 20. Capacitor C1 and C2 12 to 22 picofarad, and this is the clock select pin 011. Low frequency crystal oscillator. Look at over here. Atmega 48p, 88p, 168p, 328p oscillator is optimized for very low power consumption. And thus, when selecting crystals for maximum ESR, recommended load capacitors CL are 6.5 picofarad, 9.0 picofarad, and 12.5 picofarad for crystals. Look at over here. The low frequency crystal oscillator is optimized for use with a 32.768 kHz Watt crystal. When selecting crystal, load capacitance and crystal's equivalent series resistance ESR must be taken into consideration. Both values are specified by the crystal vendor. Now, this superscript 1, what it tells? This option, okay. Maximum ESR is typical value based on characterization. This option should only be used if frequency stability at startup is not important for the application. Okay. Low frequency crystal oscillator. The low frequency crystal oscillator provides an internal load capacitance of a typical 6 picofarad at each TOSC pin. Okay, the external capacitance C needed at each TOSC pin can be calculated by using the formula C equal to twice CL minus CS, where CL is a load capacitance for a 32.768 kHz crystal specified by the crystal vendor, and CS is the total electric capacitance for one TOSC pin. Crystals specifying load capacitance CL higher than 6 picofarad require external capacitors to be applied. Okay, the low frequency crystal oscillator must be selected by setting the clock select fuses to 0110 or 0111. Startup times are determined by the startup time fuses. Okay. Calibrated internal RC oscillator. This is the default one. Okay. Frequency range 7.3 to 8.1 megahertz, and this is the clock select pin configuration 0010. This is the recommended clock select resetting for the different frequency range. If 8 megahertz frequency exceeds the specification of the device, depends on VCC. Okay, the clock division 8 fuse can be programmed in order to divide the internal frequency by 8.
So its frequency always depends on VCC, like voltage source.
No, why? Voltage source is the, I think uh, that's different on the design. Okay, Arduino, I think Atmega 328p, they use 5 volt standard voltage operation. Okay, 5 volt. It depends, depending on the microcontroller. Some use 6 volt, some use 3.3 volt. Okay, some use again lower volt. It depends. So this is, I think, by default, the internal RC oscillator provides an approximate 8 megahertz clock. Though voltage and temperature dependent, this clock can be very accurately calibrated by the user. The device is shipped with clock division 8 fuse programmed. This clock may be selected as the system clock by programming the clock select fuses. Okay, this is the configuration of clock select fuse 0010. Okay, when this oscillator is selected, startup times are determined by the startup fuses. Okay. If selected, it will operate with no external components. During reset, hardware loads the pre-programmed calibration value into the OSCILLATOR register and thereby automatically calibrates the RC oscillator. 128 kHz internal oscillator. This is the selection pin 0010. Note that the 128 kHz oscillator is a very low power clock source and is not designed for a high accuracy. Okay. When this clock source is selected, startup times are determined by the startup fuses as shown in the following table. Okay, where at the startup? I think if you look at the data sheet, it's again in your data sheet, you will get detailed description what we are talking about. You will get detailed description in your data sheet. Low power crystal oscillator. these are the selection clock start time selection bit. There are two bit, okay, bit, okay, 2-bit, and these are the bit sequence that give you the required startup time. Startup time from power down and power set. And what are the 2 bits? Look at over here. This is the bit 2-bit. Startup bit 1 and startup bit 0. This 2-bit. Depending on the combination, 1 0 give you the maximum. Let me check. 1 0 give you the maximum. Come over here. 1 0. 1 clock. This is 14 clock. But I think if you give 1 1, you get again. If you give 0 1, crystal oscillator. For crystal oscillator, okay. For other oscillator, you see, you get different value. But for the ceramic, okay. So this is the different combination, okay, for different oscillator bit combination 1 0 0 1 0 0, and these are the delay they are giving you. So depending on your requirement, you select that particular bit combination. Particular bit combination you will select. So the table is not provided in your PowerPoint slide. It is on the data table, right? In the data sheet. The table is given in the data sheet. So 128 kilohertz internal oscillator. The 128 kilohertz internal oscillator is a low power oscillator providing a clock of 128 kilohertz. The frequency is nominal at 3 volt and 25 degrees centigrade. This clock may be selected as the system clock by programming the clock select fuses to 1 1. You see, this is the option. Note that the 128 kilohertz oscillator is a very low power clock source and is not designed for a high accuracy. When this clock source is selected, startup times are determined by the startup time fuses as shown in the following table. So where is the table again? Let's go to the table. So this is the option, okay. For the full swing crystal oscillator, I think same thing that is in the PowerPoint slide. This crystal oscillator is a full swing oscillator with rail-to-rail swing on the XTL2 output. This is useful for driving other clock inputs and in a noisy environment. The current consumption is higher than for the low power crystal oscillator. Full swing crystal oscillator will only operate for VCC 2.7 to 5.5 volt. Okay, so that's the clock select pin 011, frequency range 0.4 to 20 megahertz, and these are the recommended capacitor value in picofarad 12 to 22. We have covered these things in a PowerPoint slide. This is the 128 kilohertz internal oscillator. Look at over here. The 128 kilohertz internal oscillator is a low power oscillator providing a clock of 128 kilohertz. The frequency is normal at 3 volt and 25 degrees centigrade. This clock may be select as the system clock by programming the clock select fuses to 0010. Okay.
So nominal at 3 volt means like it's fixed at 3 volt, right?
The frequency is nominal at 3 volt and 25 degrees centigrade. This is the standard value. Okay, because they depend on the voltage and temperature. Okay, there can be some variation if this varies. Variation, okay, some variation can be. Okay, if the standard condition get varied. This is the standard condition: 3 volt and 25 degrees centigrade. So these are the startup times for the 120 kilohertz internal oscillator. This table is missing from your PowerPoint slide. Okay, that's why you have come to the data sheet. Look at over here. If you brown out detection, this BOD means brown out detection. When the voltage go low, it is called brown out, right? When the voltage go low, it's called brown out. So when the voltage go low, it is called BOD, brown out detection enable. Then start time from power down to power save, and power save is 6 clock. And additional delay from reset is 14 clock. And this is the startup time selection 00. If you do 00, startup time on time bit 00, 0 and 1, then these are the option for it. Now if you do the 01, then fast rising power, startup time from power down is 6 clock and power save is 6 clock. 14 clock additional delay from reset 14 clock plus 4 millisecond for this option 01. For option 10, you see slowly rising power 6 clock for the startup time and power down from power down and power save, and from additional delay from reset is 14 clock plus 64 millisecond.
So here 4 millisecond, is it like
4 millisecond additional delay from reset. Yes, additional delay from reset. But if you use the combination 1-1, this is reject. Okay, only 3 combination allowed. This 3 combination, but combination 1 is reject. Okay, like this is 1-1. 1-1 is reject. 1-1 is reject. External clock. To derive the device from an external clock source, EXT clock should be driven as shown in the figure below. Okay. To run the device on an external clock, the clock select fuses must be programmed 0000. Okay, this is the clock select pin at the external clock, and you can get the frequency 0 to 20 megahertz by using the external clock. When this clock source is selected, startup times are determined by the startup SUT fuses. And these are the fuse, different fuse variation. This table is missing from your PowerPoint slide. Okay, that's why you need to refer to the datasheet. And the explanation of different bit you can find from this table over here. These two bit. Startup time bit 1 and 0. So when applying an external clock, it is required to avoid sudden changes in the applied clock frequency to ensure stable operation of the microcontroller unit. A variation in frequency of more than 2% from the one clock cycle to the next clock can lead to unpredictable behavior. If changes of more than 2% is required, ensure that the MCU is kept in reset during the changes. The system clock prescaler can be used to implement runtime changes of the internal clock frequency while still ensuring stable operation. Okay. Finally, timer counter oscillator. The timer counter we have used in the week 2 lecture, timer 0, timer 1 and timer 2, you see. The device uses the same crystal oscillator for low frequency oscillator and the timer counter oscillator. Okay. On this device, the timer counter oscillator pins TOSC1 and TOSC2 are shared with XTL1 and XTL2. When using the timer counter oscillator, the system clock needs to be 4 times the oscillator frequency. Due to this and the pin sharing, the timer counter oscillator can only be used when the calibrated internal RC oscillator is selected as the system clock source. Okay, so that's the condition. That's the condition of using this timer counter oscillator. Applying an external clock source to TOSA1 can be done if the enable external clock input bit in the asynchronous status register is written to 1. Okay. So for more information, they have given you the link on page 210 and page 213 and page number 53 for more information on it. Okay, you can go to these pages for more information. Clock output buffer. The device can output the system clock on the clock output pin. Look at over here. Clock output. To enable the output, the clock out fuse has to be programmed. Okay, to enable the output, this fuse over here, clock out, should be programmed. That means you need to make this bit 0. 1 means unprogrammed, 0 means programmed. So you need to make this 0 to make this clock. The clock out fuse has to be programmed to enable the output. This mode is suitable when the chip clock is used to drive other circuit on the system. Okay, so you take the clock from this unit to another unit. Okay, the clock also will be output during reset, and the normal operation of IO pin will be overridden when the fuse is programmed. Any clock source, including the internal RC oscillator, can be selected when the clock is output on clock 0. If the system clock prescaler is used, it is divided system clock, that is output. Okay, that means it will get, you will get less value after dividing the value you get, that will be the output. Now this is the system clock prescaler. Look at over here. We talked about the system clock prescaler. We divide the main frequency by some value. So this is the prescaler. The device has a system clock prescaler, and the system clock can be divided by configuring the clock prescaler register. Okay. This feature can be used to decrease the system clock frequency and the power consumption when the requirement for processing power is low. This can be used with all clock sources output option and it will affect the clock frequency of the CPU and all synchronous peripheral. Clock I/O, clock ADC, clock CPU, and clock flash are divided by a factor as shown in the clock prescaler description. Clock prescaler register description. Okay, look at over here. This is the clock prescaler register. Bit number 7 is the clock prescaler change enable. Okay, this bit, this clock prescaler change enable bit must be written to logic 1 to enable the change of the clock prescaler bit. Clock prescaler select bit. Okay, the clock prescaler change enable bit only updated when the other bits in the clock prescaler are simultaneously register simultaneously return to 0. Clock prescaler change enable is cleared by hardware force cycle after it is written or when clock prescaler register select bit are written. Okay, so look at over here, bit position 0, 1, 2, 3, 4 bit over there. Okay, and what are the sequence we get by 4 bit? These are the, depending on the 4 bit defined clock division factor you can use. 1001 is reserved. Okay, you can use up to 256 divided by 256 up to. Okay, after that all are reserved, all other bits are reserved. So up to you can divide by 1, 2, 4, 8, 16, 32, 64, 128 or 256. Okay, that means up to then up to this. After that all the bit sequence are reserved. Suppose your frequency is 8 megahertz, and if you choose this option by default 0011, it will divide by 8. If you let's say choose this option 0010, it will divide by 4. Okay. There's another register called oscillator calibration register. You need to calibrate the oscillator to work properly, right? When you work with the device oscilloscope in your lab, what you do first? You calibrate the device. Okay, there is a built-in square wave generator with that you just do the calibration by setting different knobs. You match that built-in signal for calibration, right? Same thing. Oscillator calibration register is used to calibrate the oscillator. Look at over here, bit position 7 to 0. Oscillator calibration value. Okay, the oscillator calibration register is used to trim the calibrated internal RC oscillator to remove process variation from the oscillator frequency. A pre-programmed calibration value is automatically returned to the register during chip reset, giving the factory calibrated frequency as specified in the clock characteristics section of electrical characteristic chapter. Okay. The calibration bit 7 bit determines the range of operation for the oscillator. Setting this bit to 0 gives the lowest frequency range. Setting this bit to 1 gives the highest frequency range. Bit number 7. Okay. The two frequency ranges are overlapping. In other words, a setting of oscillator calibration 0x7f, that means all on one, gives a higher frequency than oscillator calibration 0x80. Okay, that means if you give all the value 1, 7f, okay, gives high frequency, then this value, that means this setting will give you high frequency than this setting. Okay, the calibration bit 0 to 6 bits are used to tune the frequency within the selected range. A setting 0x00 gives the lowest frequency in the range, and a setting 0x7f gives the highest frequency in the range. So this is the oscillator calibration resistor. You can calibrate the oscillator by using the resistor. Now we will talk about the power management and sleep mode. Power management and sleep mode, very important topic when you design your system for marketing. When you want to sell your product, several considerations you need to make: user friendly, power friendly. You should consume less power, and this is the area you need to explore to make your device power friendly, so that it will consume less power. Okay, so that it will run longer time with a single battery or two battery, right? So sleep modes enable the application to shut down unused modules in the microcontroller unit, thereby saving power. The device provides various sleep modes, allowing the user to tailor the power consumption to the application requirement. When enabled, brownout detector BOD activity monitors the power supply voltage during the sleep periods. To further save power, it is possible to disable the BOD in some sleep modes. Okay. BOD disable is only available for Atmega 328p. Now, what are the sleep modes? There are 5 different sleep modes we can use, right? Let me go over there. The following table shows the different sleep modes. BOD disable your ability and then wake up sources. Look at over here. 5 different sleep modes. Idle, ADC noise reduction, power down, power save, standby, extended standby. Okay. Now, there are superscripts. For some term, you see some superscript 1, 2, 3. Okay. What is the meaning of the superscript? Look at it. If you see the superscript 1, only recommended with external crystal or resonator selected as clock source. You see standby. This one only recommended, standby only recommended with external crystal or resonator selected as clock source. If you see the superscript 2, like over here, 2, 2, 2 over here, okay. If timer counter 2 is running in asynchronous mode, then that's recommended. This power saving mode are recommended when the timer or counter is running in asynchronous mode. And if you see a superscript 3 over here, superscript 3, and they're the different mode for interrupt 1 and interrupt 0, only level interrupt. Okay, during that operation, we can use those sleep mode. So to enter any, okay, there are 6, not 5. There are actually 6 sleep modes. Okay, to enter any of the 6 sleep modes, the sleep enable bit in the sleep mode control register must be written to 1, and a sleep instruction must be executed. Okay, sleep enable bit. So how is the sleep enable bit? Sleep mode control register. Look at over here. Sleep enable. This is the sleep enable bit. This is a sleep mode control register, and this is a sleep enable bit. This bit is like a main switch. It will enable or disable the sleep mode. Okay. After sleep mode is enabled, then you can use this 3-bit combination to select one out of 6 select mode. Okay. Look at over here. 3-bit combination. When they are 000, then ideal mode. When they are 001, ADC noise reduction. 010, power down. 011, power save. 100, reserved. 0101 is reserved. Okay. 110 is for standby. 1114 for extended standby. And again, standby mode is only recommended for use with external crystal or resonators. Now, the description of different sleep mode you can find on a specific block. You see, power reduction resistor, okay, standby power save mode, extended power save mode, okay. It has all the description you can find over here. ADC noise reduction mode, okay. So when you are going to implement your system, you will go through different options to find what should the maximize or maximum setting of the resistor to give you maximum power saving. And to do it, you need to program the bit of this resistor, sleep mode control resistor. Okay. And I think that's the end of our topic today. That's the end of our topic today. Let's go to your slide and let's see if there's anything else or not. Just let me go to the slideshow. So just quickly scan your slide so that we do not leave anything, okay? I think last slide. Thanks for attending. Any question?
No, sir. No, sir.
I'll upload this recording on the YouTube channel. So if you need to refer it, I can check the video. I have already given the link on your views account, my okay, channel link. Okay, in the link you will get all the video. Okay. So thank you and good luck to all of you.